Normally I give this talk with my colleague Chris Bishop, but he's out sick this week, so it's just me. So without further ado, traditional machine learning is a whole array of algorithms that have been developed over the last 40 years, support vector machines, logistic regression, neural networks. And the idea or the trick is to sort of get the right algorithm matched to your problem or your data. And one of the reasons why it's sort of a tricky, deep area is understanding all these techniques, understanding your problems, and figure out which technique to apply for your needs. But for the next little while, we're going to talk about a new approach called model-based machine learning that we're working on here in the lab. And the goal here is to have a single development framework which supports building custom models that are just tailored to your needs, your problems, your data. And it turns out to be quite powerful. So in the traditional approach, you go, how do I map my problem to an existing algorithm or tool? But with model-based approach, we go, what is the model that actually fits my problem? And so it's build a custom model that meets your needs. And as I say, we're working on a framework that I'm going to tell you about that enables all of that. So the benefits are many. So you have a model optimized for your data and your problem, as opposed to picking one off the shelf and hoping that it's appropriate, or trying many to see which is the best. The idea is also when you run a support vector machine and you run it on some data and it makes some predictions, you go, well, I think it's good, but you don't really understand how it's working. But here, all your assumptions and how the model works is expressed in a small amount of code that you can examine, and you can make improvements to the model. So it's very transparent. Everything, knowledge about the problem and the technique, it's all contained in a small amount of code. So the idea is that you could have a community of model builders. If you had a financial data problem, you may select from different models for that problem that people provide them for a fee or for free or something on the web. And so the idea is that you could build up a community of people that build these models. The other idea is in the traditional approach, generally you sort of feed your data into an algorithm and out come predictions in some way. And so the modeling and the sort of execution, the prediction making is coupled. And here you specify your model in a separate way, and the code to actually generate the predictions is generated automatically from that. So it's diverse or sort of divergent from and separate from the modeling code is separate from the execution code. The idea is that you learn one environment as opposed to learning the whole array of techniques that I showed you on the slide. And so it stops a bit of an ad hoc approach, because what a lot of people do is they're not sure which algorithm works with their data, and they sort of try many and see what turns out to be the best. But here, as I say, you're building a custom model. Before we move on, I want to make a little comment about big data. Most people, when they refer to big data, they talk about in computational size, terabytes, gigabytes, lots of data. But there's sort of two ways to think about data, both a computational size and a statistical size. So here's a plot of how the length of a piece of iron expands with temperature. And so it's actually quite a small data set. It's only 7 points. But it turns out that you can sort of fit a pattern to that. You can fit a straight line model to that, and it's quite representative. So though this is a computationally small data set, it's actually statistically quite large, because those 7 red dots actually characterize the model quite well. Conversely, and some of the things that Andrew just showed you a little while ago, if you wanted to recognize objects in images, you would even though these are images that maybe have 1 million pixels in them each and has much more data than those 7 dots, to actually do a good job of recognizing boats or bicycles or buses, you'd need millions of images, because you'd need all different sizes of buses and different shapes and from different angles and different perspectives. And in fact, Andrew didn't mention it, but in the Connect training, they train on the order of 1 million different poses. So here's an example of a computationally large but statistically small data set. One sample of each is certainly not enough to do that. And so that distinction is quite important. One of the key concepts in machine learning, and especially the model-based approach, is probability theory. You want to measure, not only make predictions, but know how certain you are that your predictions are good. I mean, you might get a weather forecast that says, well, it's going to rain today with 80% probability. And it's kind of nice to know the confidence in that. If it's 50-50, you really don't know. At the break, just to sort of remind you about probability, you're going to get a nice little handout here of some non-transitive dice. And it's kind of a fun thing, and I'll let you read about it, but it's a set of 4 dice, and you can play with another player and have your opponent pick one die out of the 4 dice. And you can always pick another die that will, in the long run, roll higher numbers. and it's a very unintuitive thing, because normally you think that if I roll this one dice and I've got this one that will roll more, if I reverse them, that someone would win. But out of the set of 4, there's always one that will roll more in the long run than the other. And it's a fun little thing. And so after the break, you can collect your own set and have fun with friends and family with that. But the message is that probability is the key to much of machine learning and quantifying uncertainty. So here's a problem that it's about recommending items, in particular, in this case, movie recommendation. So, for instance, in our Xbox Live service, there's on the order of about 10,000 movies and on the order of about 10 million users. Now, some users have said they've liked some movies, and another set of users have indicated that they don't like other movies. And so you have a subset of ratings, but there's a lot of gaps in this. It's a sort of a sparse data set. You don't really know what all users think about all movies. And so the idea is you learn from the ratings that are there, and you can make predictions on where there's gaps. And I'm going to show you a little demonstration here of a prototype system that we built. And this is just an array of movies, and right now they're not laid out in any order. And the idea is, I have to look up here because it's not on my screen, off the screen. There we are. So the idea is that this has sort of been actually trained on the Netflix data set offline, but what I'm doing now is personalizing it to things that I like or I don't like. So you could take a movie here and say, well, I don't really like that one. And what happens is these start reordering. To the right is a high probability that I will like the movie, and to the left, a low probability that I'll like the movie. And vertically doesn't really mean anything. It's just to sort of space them out so you can see them a little better. So I can take some other movie and say, well, I like this one. And if you make a few selections, it starts getting a little more certain that the idea is that some move to the left and some move to the right, because it's learning from my actions. So I can just sort of start dragging these around here, and eventually, if I sort of did this enough time, it would be more and more certain about what I'm going to like or dislike. Now, if I pick something, take this movie here, it says, it's predicting that I'm going to really like Napoleon Dynamite. So if I actually say, yes, in fact, I do like that, nothing moved very much because I didn't tell it anything new. Similarly, it sort of predicts that, I won't like Windtalkers, and if I move that there, not much happens because I told it whatever, it already knew that. But if I pick something in the middle here that it's uncertain whether I'm going to like or dislike, the whole thing kind of realigns again because I've given it new information. So the key concept here is that we can sort of not only say like or dislike, but we can associate a probability distribution with that, and give a level of certainty with our predictions. I'm just going to flip back now to our slide. All right, now I want to talk to you a little about a model called TrueSkill. In Xbox Live, it's an online gaming service, and when you log on, if you want to play chess or Halo or some other game, there may be thousands of other people waiting to play online with you. And the whole idea is they would like to match the player, your opponent, with someone who's a similar skill level to you are. So every online player actually has a skill rating, and the system to do that ranking is called TrueSkill. It's been going since the first edition of the Xbox in 2005, and it does millions of matches per day. And so this replaces the traditional system. For instance, in chess ratings to rank chess players nationally, there's a system called ELO, and it's sort of an international standard for doing this. And the idea is when you beat a player that's above your rating, you gain some points, and if you lose to someone below you, you lose some points, and if you beat someone that's close to you, you gain fewer points, and so on. But it's got a few problems in the sense that it can only work for sort of two-player matches, and it's not really applicable to teams. And a lot of the online games, there are teams and often many multiplayer games. So the idea is that TrueSkill solves these problems. But before we talk about the TrueSkill model, I just want to sort of walk through the three stages of model-based machine learning. The first is you need to build a model which represents the probability distribution of all the variables in your system. And it's often expressed as something called a factor graph that we'll see in a moment. Then the idea is you observe data, you train the system. In the case of TrueSkill, you look at games won and lost by various players. And then the idea is that you infer updated skill values. So in the graph here, the little circle is a random variable of the skill of the first player. So S1 is skill for first player. And its uncertainty in that skill is represented, in this case, by a Gaussian probability distribution. So it's got some mean shown by the vertical line and some variance or uncertainty associated with that. And that's a fairly wide distribution there. So perhaps this is a new player that's only played a couple of matches and we're not quite sure of his or her skill. And then we have a second player with a skill S2, and they also have a skill represented by a mean and a variance by a probability distribution. In this case, is a little more narrow, likely because this person's played a lot of games, and we're a little more certain that that the actual mean is their actual skill level. Now, on any given day, how a player plays may vary. Maybe they're not feeling well, maybe they're home versus away, or maybe they're just having a bad day. And so the performance, or the pi symbol there, is a function of their skill, but with a little bit of noise added in, a little bit of uncertainty added in. Similarly, there's a performance for player 2. And the idea is that you compare those two performances and you see who wins. So this is the whole model. A skill, a performance, and then some way of comparing the outcome of who wins. So then, this is our model built. Now we observe values. So we observe the outcome of the game. Let's say player 1-1, for instance. And the idea is that you then propagate messages through this graph. There's a technique called expectation propagation, where messages sort of propagate down and back up the graph. And so the whole idea is that the outcome then indicates what the performance likely would have been, which then we can update the skills. And so we can, starting with an original skill value, and if you haven't played any games, we sort of come up with an estimate, but then it's updated based on the outcome of each game. Now, one of the advantages of this technique versus the ELO technique is in convergence. So this is a plot of two actual players from Xbox Log, one gamer tag Char and another one SQL Wildman. And this is how their rating increases on a scale up to 40 over a number of games. So it takes, on the blue curve there, it takes up to 400 matches to sort of converge to the player's ultimate level. Whereas when you do the same thing on TrueSkill, it converges much, much faster. It's on the order of sort of 3 or 4 matches, and it has a pretty good indication of your skill level. And so, and this is key because, as I say, people are playing matches all the time online, and they want to sort of see instantly where they're at and have a good representation of it. So it's been very, very successful in that sense. The other thing is you can extend this basic model of 2 players to 3 players. You just, again, extend the graph, extend the model. So this is an example of sort of tailoring the model to the problem you have as opposed to sort of picking some technique that happens to match your data. So again, we can customize it for any need that you have. Similarly, you can use teams for this as well. So player 1 and 2, S1 and S2, combine, and they have a performance P1 or Pi1, and player S3 and player 3 and 4, S3 and S4 are the second team. And again, you can observe the outcomes, and again, update the skills in a similar way. Interesting experiment was done, and there is a database of all the chess matches played over time, and from literally from 1850 onward, and this data was fed through the TrueSkill model, and it's quite interesting. All kinds of game outcomes, all kinds of factors in this TrueSkill graph, and it's sort of interesting to kind of take great players of a different era and compare them to today, and all sort of calibrated against one another, because obviously some of the players overlapped in time and others didn't, but you can do it retrospectively. So it's an interesting idea. And not only that, but you can see on the purple curve to the far left, the little shaded area indicates the uncertainty. So not only do we know their rating, but we know how uncertain or that we are of how, that actual skill level. So the nice thing about probability is you kind of have a mean and a variance. You know the probability distribution, so you can quantify the uncertainty. So we know certain players are this much plus minus. Now, one of the things we're doing here in the lab is we have a framework for doing model-based machine learning called InfraNet. And I'm going to give you a quick little tutorial. So the whole idea is we saw models as a graph in these previous slides, but in InfraNet you express your model as a bit of C# code, and actually it's quite possible to do it in F# as well. And we take that model code and compile it to generate the code to do the inference, to do the message passing, to update all the random variables based on data that it's observed. And so model, we compile it, and then you feed data in, and inferences are made. So the basic steps are, much like I showed for TrueSkill, is you create a model, and that's a bit of code. You set priors, and a prior is your initial value. If you want to predict temperatures, you might know that the average temperature this time of year is a certain value. That would be a great place to start. Every other thing is, again, represented by a random variable. And then we infer posteriors, and posteriors are the output of the system. So priors are the initial assumptions going in. Posteriors are what you infer or what you compute. And we use then these posteriors to make predictions about the future. And one of the nice things about all this is the posteriors from a certain training run can be fed back as priors to the next training run, and you can sort of learn over time and improve your prediction. So, shown in a diagram form, you feed your priors or your initial conditions in, you make some observations or train the system, and you infer some posteriors, but those posteriors then feed back to make improved predictions going forward. So now we're going to look at a very, very simple problem to exemplify this. A cyclist rides to work every day, like we like to do here in Cambridge, and it usually takes about 15 minutes. And so this person sort of zooms along, goes to work, and we have a random variable in that nice little oval shape there called average time. That's a random variable representing how long it would take him to get to work typically. And its uncertainty is represented by a Gaussian or a normal distribution. But, the ride is often fraught with problems, traffic conditions and breakdowns and all kinds of horrible things, punctures, flat tires. And so we have another random variable called traffic noise, which is sort of represents the variance or the precision of the travel time day to day. And its uncertainty is a gamma distribution. So we want to learn those distributions based on observations of how long it takes to ride into work over several days, and then based on that, make predictions of how long it would take to ride in on other days. And so we can build up a little model, and this is this average time that it typically takes you to get to work every day, and the line of code in the red box is what you would write in infra.net. And most programs have variables in them that represent a floating point number or an integer. Our variables in the light blue there are random variables, and so they're backed by a probability distribution. So there's their uncertainty is represented by a distribution. And so we create a Gaussian distribution from a mean and a precision being the inverse of the variance. And we said it typically takes 15 minutes, and so that's what the 15 minutes means there, or the 15 in the line of code. Similarly, we want to model the traffic noise, and so we have a separate random variable for it, and it's a gamma. The uncertainty is represented by a gamma distribution. And then we add another random variable, which is how long it would take for us to get to work on Monday, and where its mean is taken from the average time random variable, and its precision is taken from the traffic noise. Similarly, we can add a travel time for Tuesday and Wednesday. And so the above models traveling to work over 3 days, and the 5 lines there are the infra.net code that you would write that represents that model. Now that we have a model, we can train it. So we know that on Monday that it took 13 minutes. And so we say travel time Monday is now no longer random, it's an observed value of 13 minutes. And similarly, it took 17 minutes on Tuesday and 16 minutes on Wednesday. So here's our training set. And ideally, you would do this over many, many more data points, but for the sake of the slide, there are 3. And then what we do in infra.net is create a new inference engine. And then we call infer on it, and we want, based on those observations, infer the average time distribution. And so what the 5th line of code there at the bottom says that we computed the distribution for average time. And if you look up the top left in the green, it sort of said that the average time has a mean of 15.29 and precision of 0.641. Similarly, we can infer the traffic noise distribution as well. And so now we have a more complete model, so we can start making some predictions. So here's where we were. We've trained it on 3 days. We know now an estimate of the average time and the traffic noise distributions. And we can add a 4th travel time, what the time will be tomorrow. And so we create a new random variable. Again, its average time, or its mean is taken from average time, and its precision from traffic noise. And we can now infer what it will take tomorrow. And again, you can get the mean and variance of that travel time. So this is, in a nutshell, how infra.net work. You write a little bit of code that describes your model, you feed it training data, you infer some of the distributions, and then once you know that, you can make predictions. Now, we talked about TrueSkill a few minutes ago, and this is the same or a very similar graph to what I showed earlier of the basic concept, but the idea is here's the code. So on the left, there's the S1 and S2 are the skills of the 2 players, and their uncertainty is represented by a Gaussian distribution. And then there's P1 and P2, which is the performance of the 2 players, and the performance, the mean of the performance is taken from the skill, and the uncertainty in that performance is taken from this sort of noise value beta and fed in there. And then the idea is the performance of the 2 players is subtracted, and you get a difference D, and we sort of compare that to 0. But if we assume player 1 wins, because again, this is done afterwards, we know that subtracting P1 minus P2 had to be positive. So we know that's true, and then we can sort of infer backwards and update the skills. So the idea would be that the priors would have been whatever skills you had for those players previously. You observe the outcome of the game, and then you update the skills, which are now the posteriors, and it sort of goes in a repeating cycle that every time you update the skills, that's now the prior for the next match. And so doing something like TrueSkill is 8 or 10 lines of InfraNet code. Finally, InfraNet is a huge library for doing all kinds of things, not just TrueSkill or movie recommendation, but it can do classification, clustering, modeling topics, all a huge range of problems. And also, it can work on any custom problem that you have. So I urge you to take a look at the website where you can actually download the code, read the documentation, and try it out for yourself. Right now, the library is under academic license, a non-commercial academic license, but we are using InfraNet on a lot of internal projects that will come out over the next year, and we hope to have at least commercial manifestations of it in the not-too-distant future. And that's it for now.